In 1935, Albert Einstein and his colleague Nathan Rosen published a mathematical paper that was not supposed to be about travel at all. They were trying to solve a problem in quantum theory, attempting to model fundamental particles as geometric structures in spacetime rather than as points with properties attached to them. The solution they found involved connecting to regions of spacetime through a passage in the geometry of space itself, what they called a bridge. They were not thinking about alien civilizations. They were not thinking about interstellar transportation. They were thinking about electrons. But the mathematics they wrote down that year contained within it the seed of one of the most discussed ideas in theoretical physics, and in the scientific study of what advanced alien civilizations might actually be doing, because the Einstein-Rosen bridge is mathematically equivalent to something that physicists now call a wormhole, a passage through the geometry of space that could, in principle, connect 2 points in the universe that are separated by an enormous distance in normal spacetime but that are neighbors through the bridge. And in January of 2026, a paper published in the journal Classical and Quantum Gravity argued that the Einstein-Rosen bridge is not what we thought it was for 90 years. It is something stranger, and possibly something even more significant. Start with what the bridge actually is, because the popular conception of it is wrong in ways that matter. When most people hear wormhole, they picture a tube through space, a shortcut. You go in one end near one star and come out the other end near a different star on the other side of the galaxy. The way a tunnel through a mountain is shorter than the road that goes over it. This picture is not entirely wrong as an analogy, but it captures only the simplest version of what the mathematics describes. The Einstein-Rosen bridge connects to regions of spacetime. In the original formulation, those two regions are both ends of the same black hole. A Schwarzschild black hole, when you write out its full mathematical structure, does not have a single exterior. It has two separate regions of normal spacetime, joined at the singularity at the center. The bridge is the interior connection between them. The problem, identified almost immediately, is that this bridge is not traversable. It collapses faster than light can cross it. The geometry pinches off. Any particle that enters the bridge from one side reaches the singularity before it can emerge from the other side. The Einstein-Rosen bridge, in its simplest form, is a passage that destroys everything that tries to use it. The work that changed this picture came in 1988, from physicists Kip Thorne and Michael Morris at Caltech, who asked a different question. Instead of asking whether the natural wormholes that emerge from black hole mathematics are traversable, they asked what would be required to make a traversable wormhole. What kind of matter and what kind of geometry would you need to hold a wormhole open long enough for something to pass through? Their answer was that you would need what physicists call exotic matter, material with negative energy density, which means roughly that it repels gravity instead of attracting it. The wormhole needs this material threaded through its throat to counteract the gravitational collapse that would otherwise pinch it shut. The immediate problem is that exotic matter, in the required quantities, has never been observed. Small amounts of negative energy density appear in quantum mechanics, in a phenomenon called the Casimir effect, where two closely spaced metal plates create a region between them where the vacuum energy is slightly lower than the surrounding space. But the amounts involved in the Casimir effect are negligible, holding a traversable wormhole open large enough for anything meaningful to pass through would require exotic matter on a scale that current physics has no mechanism to produce. This is where the January 2026 paper enters, published in Classical and Quantum Gravity, and authored by Enrique Gasravankumar and Joe Marto. The paper argued that the Einstein-Rosen bridge has been fundamentally misunderstood since it was formulated. Their analysis, using modern mathematical tools not available to Einstein and Rosen, suggests that the bridge does not connect to separate regions of space at all. It connects to directions of time, not the past and the future in the simple sense that those words suggest. Rather, two separate arrows of time, a forward time direction and a backward time direction, whose coexistence turns out to be necessary for a complete quantum mechanical description of reality inside a black hole. The researchers argued that the black hole information paradox, one of the deepest unsolved problems in theoretical physics, about what happens to information that falls into a black hole, can be resolved if you accept that black holes contain these mirrored time structures. The paper also suggested that this reinterpretation implies the universe existed in some form before the Big Bang. In the backward time mirror that the Einstein-Rosen bridge connects, none of this makes the original picture of a wormhole as spatial passage more physically plausible, but it suggests that the interior of a black hole is not simply a dead end, not simply a compressor that crushes everything into a singularity, but a structure with a richer mathematical architecture than anyone had appreciated. What happens inside is stranger than the conventional picture, and what stranger means, in the context of what an advanced civilization might do with a black hole, is a question that researchers are now taking seriously. Because here is where the alien question enters the physics, and it enters from an unexpected direction. The most active current scientific discussion about black holes and alien civilizations is not primarily about using them as gateways at all. It is about using them as power sources. In 1969, mathematician Roger Penrose described a process by which energy could be extracted from a rotating black hole. A rotating black hole drags the spacetime around it, creating a region called the ergosphere just outside the event horizon where spacetime itself moves faster than light. An object entering the ergosphere and splitting in two, with one fragment falling into the black hole and the other escaping, can emerge with more energy than it arrived with, extracting rotational energy from the black hole in the process. This is called the Penrose Process. And a sufficiently large rotating black hole subjected to the Penrose Process repeatedly could, in principle, yield energy on a scale that makes every other energy source in the universe look trivial. Researchers at the Dyson Mines workshop, held at MIT in 2025 and organized jointly by Penn State, MIT, and the Ultra Intelligence Foundation, convened specifically to discuss the possibility of advanced civilizations harvesting energy from black holes. The workshop, whose proceedings were published in 2026, examined what signatures such energy harvesting would produce and how those signatures might be detected. The supermassive black holes at the centers of galaxies, surrounded by actively accreting material, forming what astronomers call an accretion disk, emit energy at luminosities between 10 to the power of 44 and 10 to the power of 47 ergs per second, which is between roughly 1 billion and 1 trillion times the luminosity of the sun. If an advanced civilization were extracting energy from such a system, rather than simply allowing it to radiate away into space, they would need to build structures capable of capturing and using that output. These structures would leave a specific thermal signature in the infrared spectrum, different from the signature of natural accretion alone. The workshop identified this infrared excess as the primary technosignature to search for in the vicinity of supermassive black holes. In January of 2025, a paper published in the Astrophysical Journal took a different approach to the same question. Shante Bagram and collaborators proposed that advanced civilizations, particularly those dominated by artificial intelligence, might use primordial black holes as their primary energy source. Primordial black holes are hypothetical objects that may have formed in the very early universe, in the first fractions of a second after the Big Bang, before any stars existed. They would not be remnants of stellar collapse. They would be direct products of density fluctuations in the primordial plasma. Their masses could range from much smaller than stellar black holes to much larger, and they would have been distributed throughout the galaxy long before any solar system formed. The paper proposed that advanced civilizations would build Dyson sphere-like structures around primordial black holes, capturing the radiation that these objects emit as they slowly evaporate through a quantum mechanical process called Hawking radiation. The paper also proposed a specific observational signature: excess infrared and submillimeter radiation concentrated around locations in the galaxy, where primordial black holes would be expected to concentrate. This is not a confirmed observation. It is a prediction that tells astronomers specifically what to look for and where. And then there is a thread in this conversation that is purely speculative, but that physicists take seriously enough to publish about: the ER equals EPR conjecture. In 2013, physicists Juan Maldacena and Leonard Susskind published a paper arguing that the Einstein-Rosen bridge connecting to black holes is mathematically equivalent to the quantum entanglement connecting to particles. Up equals EPR is how it is written. Einstein-Rosen bridge equals Einstein-Podolsky-Rosen entanglement. If this conjecture is correct, then every pair of entangled quantum particles in the universe is connected by a microscopic wormhole. Not a wormhole you could travel through. An infinitesimally small geometric connection in the fabric of spacetime. The conjecture, if correct, would mean that wormholes are not exotic, rare, or hypothetical in principle. They are ubiquitous. Every act of quantum entanglement creates one. The question of whether these connections could be enlarged, stabilized, or used for any form of information transfer is a question that the conjecture itself cannot answer, and that the physics of quantum gravity, which does not yet exist as a complete theory, would need to address. But the conjecture suggests something that is at minimum worth taking seriously: that the deep structure of quantum mechanics and the geometry of spacetime are more intimately connected than anyone understood before 2013, and that the connection between them runs through exactly the kind of structure that the Einstein-Rosen bridge describes. Here is where all of these threads converge into a picture that is still incomplete, but that is far more scientifically concrete than most popular discussions of black holes. As gateways acknowledge, the original picture of a traversable wormhole requires exotic matter that has never been observed in sufficient quantities. The January 2026 reinterpretation of the Einstein-Rosen bridge suggests that what is inside a black hole is architecturally stranger than the conventional model. The Penrose process and the accretion disk energy make rotating black holes the most powerful energy sources available to any civilization in the universe. The MIT Dyson Mines workshop has produced specific observational predictions for what a civilization harvesting black hole energy would look like from the outside. And the ER equals EPR conjecture connects the geometry of wormholes to the quantum physics of entanglement at the most fundamental level. None of this adds up to proof that black holes are gateways. What it adds up to is something different, and in some ways more interesting. It is evidence that black holes are the most physically significant objects in the universe for any civilization that has reached a level of technological development beyond what we currently possess. They are the densest energy sources. They are the most mathematically complex structures. They may be, through the ER=EPR connection, intimately linked to the quantum foundations of how information is stored and transmitted in the universe. And any civilization that has had billions of years to study and exploit the universe's physics would have arrived at black holes, not as objects of scientific curiosity, but as the central infrastructure of everything it does. If there is any place in the universe where the signature of advanced alien activity would be concentrated, it is not orbiting a temperate, rocky planet in a habitable zone. It is in the extreme environments around the objects that contain the most energy, the deepest mathematics, and the strangest physics that the laws of nature allow. And the strangest physics that the laws of nature allow has always, in the end, turned out to be exactly the physics that the universe was already using.